Here's a deceptively simple expression that's caused more internet arguments than you'd expect. Go ahead, try working it out. What answer do you get? If you got 10, that's completely reasonable. If you got 58, that's also perfectly valid. Wait, how can that be? Well, that's exactly what we're going to explore because this isn't really about arithmetic at all. It's about something much more fundamental, how mathematical notation itself communicates meaning. When we look at a mathematical expression, we need some way to agree on how to read it. These rules are called the order of operations, often remembered by the acronym PEMDAS or BODMAS. But here's something that might surprise you. These aren't universal mathematical truths. They're conventions, agreements we've made about how to parse mathematical language. PEMDAS stands for parentheses, exponents, multiplication and division, then addition and subtraction. Now, most of us learn that multiplication and division have equal priority, so we evaluate them from left to right. But here's where things get interesting. This left-to-right convention isn't as universal as you might think. Different mathematical communities have actually developed different approaches to this over time. Let's start with the approach you probably learned in school. When operations have the same priority, we work from left to right. Here we have 6 squared, divided by 2 times 3, plus 4. Following PEMDAS, we start with anything inside parentheses. The parentheses just contain 3 by itself, so there's nothing to calculate there. But notice, those parentheses are sitting right next to the 2, indicating multiplication. This placement is actually at the heart of our controversy, but let's follow the standard approach for now. Next up, exponents. First, we handle 6 squared. 6 times 6 is 36. So now we have 36 divided by 2 times 3, plus 4. And here's where things get fascinating. We have division followed by what looks like multiplication. Under the standard school approach, we treat this implied multiplication, where the 2 is just sitting next to the parentheses, as having the same priority as explicit division. So we work left to right, division first. But this is exactly where the disagreement starts. 36 divided by 2 gives us 18. Now we multiply 18 by 3. That's 54. Add 4, and we get 58. So that's one way to read this expression. But there's another way to read this expression that's equally legitimate mathematically. This isn't about someone making an error. It comes from a different convention for handling what's called implicit multiplication. Let's see where this leads. We start the same way. 36 divided by 2 times 3, plus 4. But here's where this interpretation diverges. Instead of reading left to right mechanically, there's a tradition of seeing something deeper here, implied grouping through juxtaposition. The idea is that when terms are written right next to each other, what we call juxtaposition, they form a tighter bond than explicit operations do. This isn't just some arbitrary rule. It actually reflects how mathematicians intuitively read expressions. Let me show you what I mean with an example from physics. In physics, when you see 1 over 2 pi r squared, every physicist reads this as 1 divided by the entire quantity, 2 pi r squared. Nobody would interpret it as 1/2 times pi r squared. The fact that 2 pi and r squared are written together creates natural grouping. They stick together as a unit. So from this perspective, we're looking at 36 divided by a single unit, 2 times 3, rather than a chain of separate operations. Back to our problem. If we apply this principle of stronger binding, 2 times 3 becomes a single unit that we evaluate first. 2 times 3 gives us 6. So now we have 36 divided by 6. That's 6. Plus 4. And we get 10. So we have 2 completely reasonable ways to read the same expression, leading to 2 different answers. But here's the key insight that resolves what seems like a paradox. Here's the key insight. This isn't really about order of operations. It's about ambiguous notation. Both interpretations we've seen are perfectly logical. The real solution isn't picking the right rule. It's writing mathematics that can't be misunderstood. If you mean 58, write it like this with parentheses. If you mean 10, write it like this with parentheses. The takeaway: good mathematics isn't about memorizing obscure rules. It's about communicating so clearly that no confusion is possible. I hope this gave you a new way to think about mathematical notation and communication. If you enjoyed exploring this question that goes deeper than it first appears, I'd appreciate a like, and consider subscribing if you want more videos that look at the beautiful subtleties hiding in mathematics. Thanks for watching, and I'll see you next time.